So in the previous video we have seen the different formula and the units associated with working on the problems of chapter 12, that is electricity. Right, let us work a few example problems and also the exercise problems. Okay, right, so let us start with some of the example problems. So okay, we work example 12.1 example 12.1 of page number 200 of our book. Right, okay, now a current of 0.5 amperes is drawn by a filament of an electric bulb for 10 minutes. Now, okay, find the amount of electric charge that flows through the circuit. So, how much is what is that charge flowing? And given, he has given us what is called as so we write down given. Given it is the amount of current, that is I, is equal to 0.5 ampere, and 1 is the time for which this has gone. So the time taken is 10 minutes. Okay, right, so that is 10 minutes. Right, okay, now let us work out these amperes, that is in minutes, so convert that into seconds, because ampere second is what is called as coulomb. Right, so that's how I have to change this into what is called as seconds. Right here, 10 times 1 minute I know is 60 seconds, so I write 60 seconds, that is 600 seconds of time. Okay, so we have this. Right, okay, now what should I do? So I use the formula for current. So I know by definition current is the rate of flow of charge. So stick on to the basic, children, so you don't have to ponder for the question, right? Okay, you don't ponder for the question, the formula, but just stick on to the basics. So what is the relation between current, charge, and time? So we know that the definition is current is equal to charge flowing per second, I equal to Q by T. So stick to it and what you get, right? Okay, so that is I equal to Q by T. So naturally Q will be equal to transpose, and we will get I times T. So that is I is 0.5 ampere, and the time is 600 second. That becomes 5 times 60 per second. That is nothing but coulomb of charge, and 200 coulombs of charge. So that is what you will do, right? So children, right, here we have in text question number 3 and page number 200. Now, number of electrons. So what is he asking us? In the question, he is asking us the number of electrons in 1 coulomb of charge. So what is the number of electrons in 1 coulomb of charge? Now I know that the charge on 1 electron, so charge of 1 electron is 1.6 into 10 power minus 19 of coulomb. And what is he asking us? He's asking us how many electrons are there. So that is right. Okay, 1 electron charge is that much, that many coulombs. So that is 1 coulomb will be equal to 1 electron, 1 by 1.6 times 10 power minus 19 of electrons. Okay, so what that becomes, children? So that will be 10 power 19 divided by 1.6. So that is 10 power 20 divided by 16, and that will be equal to 100, say, times 10 power 18 divided by 16, and 16 6 96, and point, and 16 230. Right, okay, 16 6 96, right, okay, good, and 96, that's 4 remaining, and 16 is 32, and 16 is 18, so that becomes 6.25 into 10 power 18 electrons. Okay, so 1 coulomb of charge thus has what is actually 6.25 into 10 power 18 electrons. So this is the number of electrons that are there in 1 coulomb of charge. So children, we're going to work some problems related to the potential difference, right? Okay, so example 12.2, page number 202. So what's the question? Let's quickly read out. How much work is done in moving a charge of 2 coulombs, right? Okay, 2 coulomb charge is moving across 2 points whose potential difference is having a potential difference of 12 volts. So what is given to us? So we are writing given, what is given? So the charge flowing is 2 coulombs of charge flowing and past 2 points past 2 points which are having a potential difference of 12 volts. So okay, right, is it 12 volts? Yes, it's 12 volts. Now what is it that we have to find? What is that we have to find? How much of work is done? So okay, right, go to the basic potential difference. We know potential difference is equal to work done in current unit charge. So that's the idea, right? Okay, just I want this now. So what do I do? V into Q transpose, and we will get W equal to V into Q. And what is V, children? That's 12 volts, and that is 2 coulomb, and that is 24 volt coulomb. That is joule of energy. Unit of work is joule. So that is the amount of work done or the energy supplied. Okay, right, children? So there we are. So to write, we will now do page number 202, that's in text question 2. So what is that? What is the meaning of 1 volt? Right, okay, now go back, if you have the definition, by definition, 1 volt. Now what is the meaning of 1 volt? Okay, right, if you have no idea about what 1 volt is, just go back to the basics, potential difference, PD is equal to W by Q, right, okay? So that is V equal to W by Q. Right, okay. So if it is 1 volt, now if it has to be 1, so this has to be 1 and that has to be 1. So what is the meaning of it? The meaning is, the meaning of this is, it is, it is 1 joule and 1 coulomb. So what is the meaning of this one? So this means that, right, so the potential difference between 2 points is 1 volt, 1 volt when 1 joule of work is done in carrying a charge of 1 coulomb across 2 points. So okay, right. So there are 2 points, A and B, and you are working in order to make a charge of 1 coulomb move from here to here. So if at all, in order to move that, 1 joule of work is done, then we say the potential difference is equal to 1 volt. So that's the meaning of this 1 volt, children, for your information. Right. So children, right, we go to in text question number 3 of page number 202. So what is he asking us? He's asking us how much energy is given to each coulomb of the charge passing through a 6 volt battery. So the battery's potential difference given the PD is or PD of PD, or the electromotive force inside actually. So V is equal to that is how much is that, children? So it is 6 volt. The battery's potential difference is 6 volt, or electromotive force is 6 volt there, and the charge is moving now. Okay, the charge here is 1 coulomb charge is moving between 2 points. That is between 2 points now. Okay, right. So how much of work is done, or how much of energy is required to move the charge? So it's like this terminal, this is a terminal, and that's another terminal, right? So charge is flowing between these, okay, right, between the terminals of the battery. So that's the battery, and okay, right, how much of energy or chemical energy is utilized in order to make 1 coulomb of charge from here to here if the potential difference between the 2 terminals is 6 volts. That's the idea, right? You can again go back to the basic. What is the basic? The basic is again the same formula. Potential difference or the electromotive force here is equal to W by Q, and W indicates the amount of energy. Again, V into Q, that will equal to what is V, children? That's 6 volt into 1 coulomb, that is 6 joule energy. So that 6 joule of energy is required. So children, there we are. So children, right, let us now work the problems related to resistances involving Ohm's law and resistivity. Okay children, so those are the problems that we'll be working now, and let's see what the problem number 12.3 or page number 208 gives us. Right, okay, now let us see children, there are two parts in this problem, A and B. Let me read the first one, and we'll work the first one first and then next the other one. Right, okay. How much current will an electric bulb draw from 220 volt source if the resistance of the bulb filament is 1200 ohm? So okay children, right, we have the source of potential difference given. What is given to us? The source is having a potential difference of how much is that? 220 volts. So that is 220 volts. And the next, what is given next children? And the bulb filament, okay, right, and the bulb filament, the resistance of the bulb filament is 1200 ohm. So the resistance we know that is divided by R, and that is 1200 okay, 1200 ohm omega. Okay, what is he asking? Well, how much of current is going through this filament? And the voltage is that, and the resistance is this. Right, okay, so that's what children, and we have to find the current. So we have to find the current. So right, okay, so that's what we have to find. Now how do we do it? So children, if we are just thinking about what formula to use, don't think much, just get the general rule of Ohm's law, right? That is children, V equal to IR. So even if you don't remember that, just remember this triangle children. So at the vertex we have V, at the vertex V, and I here, and there are, so they're both at the base, both I are at the base and V at the vertex, because Ohm's law is related between is the relation between V, I, and R. Don't forget about the remaining things. Right, okay, now V equal to I R. So what is that? You are to find I. So just this you are to find, remaining that is V by R. So just write V by R, that is V is 220 volts by 1200, that is gone, and that is 11s and 260s, that's 11 by 60. I'm going to divide that 11 by 60, so that becomes 0.61, so 60, that's 5, 0 and 0. 6, 8 times is 480, that is 20, and here 6 trees as 1800. So that's going on, and that will be approximately 0.183 ampere. So let's write it 0.188 ampere. So I'll calculate your current. So there we are. That's the first part of example 12.3. Now we move to the next part. How much current will an electric heater coil draw from 220 volt source if the resistance of the heater coil is 100 ohm? So the same children here, given what is given to us, the voltage source is 220 volt, and the resistance of the coil is heating coil is 100 ohm. And what is that we have to find, children? Again the same thing. What is that we have to find? So again we have to find the current here. So just like this, and we employ the same thing. I equal to V by R, that is V is 220 divided by 100, that will become okay, right, that is 2.2 ampere. Okay, so there we are. So this is how we calculate the second part, right? That's 2.2 ampere current. So children, right, let's now work example 12.4. So what's that? Reading the potential difference between the terminals of the electric heater is 60 volts. So right, okay, 60 volts, and that's drawing a current of 4 ampere from the source. And the current, what current will the heater draw if the potential difference is equals to 120 volts? So it's a simple problem related to Ohm's law. That is we are increasing the potential difference. The conductor is same. Indirectly we have the same resistance for the conductor. And what is changing, children? So the current has to change because we are changing the potential difference. So when the potential difference is doubled, the current also should be doubled according to Ohm's law. So what should happen now? So that should become so 4288 ohm. So that is a quick thinking, but when you work the problem, we work it this way. Now given, right? So given the condition 1. Alright, what is the condition 1? Okay, right, and that's the second condition. Okay, right, so condition 2. So we have V, that is potential difference, equal to, what's the potential difference shown? That is 60 volts. Okay, 60 volts, and the current is, how much is that current shown? That's 4 ampere. 4 ampere, that's very good. And we are calculating the resistance because resistance is what is common here, and this resistance will carry here. So right, and he gives us the potential difference will become 120 volts, and he's asking us what the current is. So we calculate the resistance here, transport it there. So okay, right, so what should we do? So we'll employ this magic triangle. So right, so at the vertex V, the potential difference I, and R the place. Okay, right, so R is equal to V divided by I. R equal to V divided by IV. 60 by I is 4, that becomes 15. So R is equal to 15 ohm resistance. Okay, that's good. And carry it here will become 15 ohm there indirectly. So I'm carrying it here. And what is I? So again, employ the Ohm's law. I equal to V by R. So I calculate this I. That will be by R. So it become I equal to V by R. So what is V? V is 120 divided by what is R is 15, and that becomes 54, 16, 8, 120, so 8. So I equal to 8 ampere. So there we are. In this case, the current is doubled when compared to the because it is keeping in line with Ohm's law. What is Ohm's law? Ohm's law states that potential difference is directly proportional to the current. Or current flowing in a conductor is directly proportional to the potential difference. As potential difference increases at the same rate, what happens is the current also increases. As the potential difference here is getting doubled, the current will also will be doubled. Now, okay, children, right, let's go to example 12.5. So children, example 12.5. So let me read out the question for you. Resistance of a metal wire. There's a metal wire of length 1 meter, and that resistance is 26 ohm at 20 degrees Celsius. Okay, if the diameter of the wire is 0.3 millimeter, okay, it gives us the diameter. What will be the resistivity? So what we have to do is we will calculate the resistivity of that conducting material of that wire, right? Okay, next one. And apart from that, he says using the table 12 to predict the material of the wire. So how do we do it? Just find out the resistivity of that material and check that in the list, and whichever is correlated similar or just merely equal to, that is the material that we will come to conclude that is the material of that particular metal one. Right, okay, so children, let us quickly take down these values and start working with this problem. So children, right here we are. I've taken the values. Length of the wire is 1 meter, resistance of that conductor is 26 ohm, and the diameter of the wire is 0.3 millimeters. So okay, right, resistivity, it will come out to be ohm meter. Units will be ohm meter, so the whole thing should be in meters. So what I do is I convert that into meters. So 0.3 milli, that's 10 per minus 3 times meter. So that is 3 times second, right? That's 10 per minus 1. So 10 per minus 3 becomes 3 times 10 per minus 4 meter. So that's the diameter. Now, okay, what have we to do is diameter. So children, let us calculate the radius of this wire, because we'll calculate the area. So we have the length, we have the resistance. For resistivity, we need we are calculating resistivity. Resistivity is R times A by L. So okay, right, we don't have the area, so we are calculating the area here. 3 times 10 power minus 4 divided by 2, that will become 1.5. So is equal to 1.5 times 10 power minus 4 meters. So what have we to do with radius here? So we'll calculate the area of cross section of the wire. So naturally, the wire is expected to be cylindrical. So alright, the area of the wire will be area equal to pi times r squared. That is 3.14 times r. What is r, children? So it's 1.5 times 10 power minus 4 whole square. That will be equal to 3.14 times 2.25 times 10 power minus 8 meter square. So that is the area. Okay, that's very fine. So the area, right? Okay, but multiply that, it will come out to be 3.14 times 2.25. That will become 5 plus 20 is 0, 2, 5 1 5 7. That's good. 5 3 is 15. That's okay. 2 4 is 8. 2 1 is 2. 2 3 is 6. That's good. And that becomes 6 2 8 again. That's 0 5 1 5 6 8 8 16 6 1 6 2 8 9 10 0 1, and that's 7. So it become 1 3 4. So it becomes 7.065. So area is I just write the area cross section is the area cross section is 7.065 of square meter. Right? The area, that's the area. Now, okay, employ all these things that we have got here, and we'll write down, children. So rho equal to r times a by l. What is r? That's 26 times a. What is a? So we found that 7.065. Okay, right. Divided by l is 1. So it is simply 26 times 7.065. That many ohm meters. So okay, what would this be? So 7.065 times 26. 26 5 is 130. 0 13. 26 6 is 156. 159, 169, and 16. And that becomes 6 and 1. 26 7 is 740, and 7640 to 182. Right, okay, so 26 times 7, so that becomes 7640 to 24, 7 is 14 and 18, so it becomes 182. Right, okay, 180 to 183, so approximately 183 is approximately 26 7. Okay, right, 183, so it becomes so there we are that 3 times. Okay, right, good. So there we are, and that is 183.690, or simply 69 times that becomes okay, sorry, so I should have placed area as 10 power into 10 power minus 8 meters square here. So alright, 10 power minus 8 meters square here, it becomes 10 power minus 8, that is 10 power minus 8, so it becomes 1.8369 times 10 power minus 2, so that's 10 power 2, and the 10 power minus 8, that becomes 1.8369 times 10 power minus 6 ohm meter. So that's the resistivity. So we calculate it. So it's approximately 1.84 times 10 power minus 6 ohm meter. When I check the list of those characters or conductors of all the materials, I find that this matches with manganese. So the material of that wire is the material of the wire is manganese. Okay, so right. So there we are. We have manganese, right? Okay, now let us go ahead to work the problem 12.6 of the examples, right? So children, right, let's now go to example 12.6, and let me read out for you. A 4 ohm resistance wire is doubled on it. So doubled on it. So calculate the new resistance of the wire. So what we are doing is we are taking a wire of certain length, we are doubling it. In order to double the same wire, we have to bend it, or right at the middle it is folded to, so that the wire's length becomes half and the area of cross section gets doubled. So that's as easy to understand. So we have doubled the wire. So it's like this too. So I want you to understand it. And so there's a wire and of certain length, and there we are doubling that. So if the area of cross section is A and we are doubling it, so naturally what will happen to the wire? So okay, where we are folding it, so the wire gets doubled. So the area of cross section becomes 2 times the area, and the length becomes the half of the length. So if area is A1 and that's L1, and here the area is A2, that becomes double A1, and the length it is L2, so that becomes half of L1. Okay, children, right there we are. This is what is the understanding. And what should we do? Here we find out the resistance of the wire. But one thing is common for both the wires. What is that? Resistivity of the materials is same. Resistivity of the materials is same. So that's what, children. So we have the first condition. So we just take the first condition 1 like this. Condition 1, or otherwise we write the original wire, and the changed wires. Just distinguish between the two conditions. I'm writing like this. There's nothing changed wire or anything, but we have folded it, so the dimensions have changed. Right, next. Okay, now what is the length? What is the length of the wire? So that is L1. What is the area of the cross section? So that is A1. Now what is the resistivity? Resistance. What is the resistance? Resistance. That's R1, that is calculated. It is nothing to calculate, it's already given. So that is 4 ohm. So that is 4 ohm. Now, what is changed here? The length, let us call it as L2, that is half of L1. Otherwise, I write it as L1 by 2. Okay, good. And the next one, what happened to the area? Area A2 is has double this quantity, so it becomes 2 times A1. Now the resistance, so you calculate what the resistance is. What happened to the resistance? You're not children something here. As the length is decreasing, resistance should increase. That's one. And as the area of cross section also is increasing, as the area of cross section is increasing, resistance should decrease. Okay, so children, length decreases, resistance decreases, area of cross section increases, resistance decreases. So by rule. Okay, so that is the relation. The next one, right? Now, so there is a calculator. Now, for both of them, the resistivity is same. So all right, resistivity is R into A by L by the relation. Even if you don't remember this relation, it's quite easy to just go to the basic principle. That is, resistance is directly proportional to length, and the resistance is inversely proportional to area. Club both of them, and you get resistance proportional to L by A, and there gives resistance to L by A. Transpose things, and you get the value of a rho. So don't break your head to mark the relations or the formula individually, but just remember stick to the basic principle, the basic idea. You get all those things. Now follow carefully. So let me write it as R1 times A1 times divided by L1, and here I write it as rho equal to R2 times A2 by L2, because it's the same material. Resistivity will be same. So this is first, and that's second. So what would that be, children? So R1 into A1 by L1 should be equal to R2 into A2 by L2. Okay, right. So what will happen now? So just employ these values there, and you will get the value of R2. So what is R1? So children, it's better for us to calculate here. So R1 is 4, right? Good. I have written 4. That's fine. R1 is 4. And the next one, what is A1? That is right, A1. And that is L1. Okay, right here. And R2, we are defined of R2. And the next one is A2. It is 2 times A1. And what is L1? Is half of. So I mean, what's L2? L2 is half of L1. So I'll write this again as L1, that is equal to R2 into 2A1 times 2 divided by L1. So that will be equal to 4 times that's R2 into A1 divided by L1. That will be equal to 4 times A1 by L1. And there you are. L1 divided by A1 divided by, and you'll get 4 is equal to 4 times R2, or R2 equal to 4 by 4. That will become 2 equal to 1 ohm. So what we see children, so there is a decrease in the resistance. So children, so there is a decrease in the resistance. Okay, so that's what children. So area is increasing and the length is decreasing. So overall, the aggregate, the equivalent resistance has decreased. The effective resistance has decreased, I should say, because of decreasing in the area. So increasing the area and decreasing the length. So children will be working the many more problems again in the next part of the video. And what I want you to do is practice these examples. The reason why I have done this extensively is elaborately is only to make you understand the basic behind this. So you just can do switch in a switcher, but the thing is, as this video is made to with the point that the people or the children should understand this easily. So hope you have enjoyed this video, children, and I will produce a few more videos related to these problems and not only the examples but also the exercises. Okay, children, thank you very much.